It's a pleasure for me to present my work in my university. I'm a second year PhD student from Scuola Superiore Meridionale and Astronomical Osservatory of Capodimonte. And actually I'm doing my studentship at ISO Garching. My PhD project is based on the use of Type II and Anomalous Cepheids as an alternative route to the Hubble constant. As also my colleagues this morning talked about, we know that the Hubble tension, the phi sigma tension, is between measurement coming from the early universe and the late universe, whereas there is no contact point in phi sigma between the confidence interval of these different measurement of each node. The most accurate measurement of each node from the late universe is based on the 3-run Schu's extragalactic distance scale that allows us only in the third run, that is, thanks to supernova 1A in the Hubble flow, to measure each node. But the distance ladder begins very close to us. Indeed, the first step is the calibration of the period luminosity relation of classical Cepheids. We can see here that on the x-axis we have the geometric distance. Indeed, we choose systems of which we know the geometric distance from with different methods. In the Milky Way, we have the Gaia parallaxes. In LMC and in M31, we have the eclipsing binaries. And in NGC 4258, we have a maser. But the powerful tool is that on the y-axis, we have the distance modulus of Cepheids that we can obtain since we observe an intrinsic luminosity for a Cepheids, and thanks to the period luminosity relation, we add the absolute magnitude and we derive a distance modulus. Here we can see the first plot of a period luminosity relation that was presented in 1912 by Miss Leavitt. She noticed a correlation among the maximum and minimum of Cepheid liqueurs in small Magellanic clouds with their period. And she also suggested that probably period is linked with the stellar parameters. And I also want to let you know that period is not linked with the systematic errors of photometric measurement, absorption, nothing. But as soon as Leavitt presented this relation, it was used by Hubble in 1925, since Hubble observed some Cepheids in the direction of Andromeda, and as we can learn here in his article, he decided for more detailed investigation to plot the maxima against the logarithm of period. And he found out that Andromeda and M33 were far from us of 300,000 parsec, and the same Hubble, in a public lecture in Washington, he confirmed that probably we are in a theory of island universes, and that our universe was not only the Milky Way. But as soon as Hubble confirmed this, he also raised a doubt, that is, while astronomers are not clear as the causes of this relation, they believe that it holds for every Cepheids. In 1958, Sandage, assuming that the observed scatter of the period luminosity was not only due to photometric error and absorption, introduced a third parameter, the color, and he suggested that indeed the relation was a period luminosity color relation. Why we can assume this? Because if we took a pulsating star and we assume that the pulsation is a global radial oscillation, we can link the period with the density of the star. Then we know that we have a Stefan-Boltzmann law for a star, so we can link the density with the luminosity, the mass, and the temperature. And in turn, for a pulsating star, we have that the period is linked with as a function of mass, luminosity, and temperature. But we also know that there are two important parameters in the life of a star that are mass and chemical composition, and we will see later how this chemical composition influences our period. Then, so we have this function, but we know that from evolutionary theory that at a given evolutionary stage, mass is not independent from luminosity, so we can eliminate this parameter, and we have the well-known, we have the period luminosity color relation that becomes with observable quantity a function of period is a function of the observed magnitude and of a color. But you can also notice here that I'm not using the gamma term in this equation, and you will discover later why. Whereas this is the form in which we astronomers nowadays use the period luminosity color relation, where alpha is the 0 point, the one that we need to calibrate to start the extragalactic distance scale, beta is the slope of the relation, and delta is the coefficient of the color. So we have learned that the period luminosity color relation is what defines the so-called Cepheid manifold. So that is the place, the locus where we can find Cepheids. And I want to stress you that period luminosity color relation holds for each individual Cepheids, because once we know the period and the color, we will obtain an absolute magnitude for the Cepheid, and we will have a distance. Whereas, as we can see here, the period luminosity relation is only the projection of this plane on the plane log L log P. This means that the period luminosity relation is an average of over the extension of the color. And this is the form in which we use the period luminosity relation, and this is the standard candle of the first step of the distance scale. But from this Cepheid manifold, we can learn also where Cepheids live. Indeed, we can see that the plane log L log T is a color magnitude diagram. And if we project the PLC plane on this plane, we will obtain the so-called instability strip. That is the locus on the color magnitude diagram where Cepheids and all the radial pulsator stars live. And I want to stress you that once we observe a star in the instability strip, we gain another observable, that is the period, that is linked also, as we see, is linked with the stellar parameter and has no problem with the is not linked with the photometric errors and so on so far. So just to do a little step back, we can see what's happening for a pulsating radial star. Indeed, this is what we see when we observe a Cepheid. We observe changes in the radius and changes in the temperature. And what causes this is a change in opacity. Indeed, the external layers of the star are partial ionized, and they are not allowing the energy coming from the inside of the star to go outside. So there is a surplus in energy, and this surplus will allow pulsation to start. And this mechanism this mechanism, we can observe this mechanism when a star is inside the instability strip. Now, let's see what are the kind of stars that populate the instability strip. I talk about classical Cepheids that nowadays are the ones that are used in the extragalactic distance scale, and they are population 1 indicators. So, as also the previous speaker said, we can find them only in spiral galaxies. But the strip is also populated by RR Lyrae, that are population 2 distance indicators, and by Type II Cepheids and Anomalous Cepheids, that are, I'm using these 2 distance indicators because they are they can provide an alternative route. So, since these are different populations and cross the stability strip of different luminosity and a different period, this means that they will follow different period luminosity relation. Indeed, here we can see that different different pulsating stars follow different period luminosity. But I want also to stress you that also classical Cepheid, fundamental and first overtone, they follow 2 different period luminosity relations, and that these are all different age pulsating stars, and we should not use the same PL to not have a each node of 600 megaparsec because they were confusing population 2 and population 1 distance indicators. At this point, we know that period luminosity can be used as distance indicators, but we also know, as previously announced, that there are some problems that are the width of the PL, the extinction, and the metallicity. Why we should take this into account? Because, as I told you, the period luminosity is a projection of the period luminosity color. So this means that we should know which is the angle that reduce the scatter. And this angle is linked to period. And moreover, the average, as every physical quantity, is linked to number of points that are populating our period luminosity. Whereas we should also know that when we receive a light from a Cepheids, this light is extincted, and if we want to take this into account, we should know stellar atmospheres, extinction law, and instrumental filter response. For this reason, nowadays, we are using in the extragalactic distance scale the so-called Period Wesenheit function, because as we can see here in this plot by VISTA and T, the period Wesenheit is the red one on top, and we can see that the intrinsic scatter is 5%. This means that this is a good combination to reduce the intrinsic scatter, and we only need to know an extinction law. So period Wesenheit is a win-win because solve the problem of the wind of the stability strip and the problem of the extinction, but we have the last problem, that is the metallicity. As I told you, we were missing a gamma term, and this gamma term is because we used this to define how much the metallicity of a star influence is path to the stability strip. Because when we have for a given mass with a different chemical composition, the star will enter the stability strip at a different luminosity. This means a different period. So theory predicts this, and also observation confirms this, since every star with a different color means different metallicity. And we can see that this also gives a scatter to the relation. Nowadays, this is the situation of how much the gamma term for classical Cepheid influence the value of each node. We can see that all the values with a different gamma term are in agreement within 1 sigma, but if we want to reach the accuracy of 1%, we need to take into account every source of systematics and differences. So my project is this is the context of my project, because we aim in my PhD project to calibrate the different period luminosity and period Wesenheit relation for these two different kind of pulsating stars. We want to also to quantify for the first time the gamma terms thanks to Formos spectra. We want to calibrate these thanks to Gaia for parallaxis, and so we will be able to compare a local distance scale for different classes of pulsating stars to search in for systematics. My project started with my master thesis, in which I analyzed Type II Cepheids and Anomalous Cepheids in the large and small Magellanic Clouds, observed in the context of the VISTA Magellanic Clouds survey. And the first things that we did was to define some templates, because as you remember, I told you that period luminosity relation started with luminosity at maximum and minimum. And nowadays, the technique that we use is to from the best light curves, of which we have more than 12 points, we retrieve a template, and then we use this template to calculate the magnitude for light curves that are not well sampled. So these are some examples of light curve for Type II Cepheids and observed period luminosity relation. Then I fitted this, that means that we did the average, and we presented an extensive catalog of period luminosity and period Wesenheit going from the optical to the near infrared bands, and we used this to calculate, once we calibrated with the geometric distance of LMC, to calculate the distance of galactic globular cluster. And we see that the distances based on Type II Cepheids are smaller than the literature one. This means, in turn, that if we want to use this distance to calibrate the tip of red giant branch, could probably affect the value of each node. Whereas, in my last work, I started analyzing like curves for anomalous Cepheids, and as you can see here, anomalous Cepheids can pulsate both in fundamental and first overtone, and they follow two different period luminosity relation, and I fitted for the two different subsamples, but also for the first time I found that a value to fundamentalize the first overtone pulsator for anomalous Cepheids. This means that we can improve the statistics of the period luminosity relation, and so we presented all these values for the 0 point and the slope for the anomalous Cepheids in LMC. And in this case, to check the validity of this relation, we decide to calibrate them with the Gaia parallaxes and to compare to calculate the distance of LMC. And as you can see here, you know that also for classical Cepheid, Gaia parallaxes are affected with a problem of 0 point, and we need to apply a counter 0 point offset. And we see that also for anomalous Cepheids that trace a different population, they have different period luminosity, we need to apply the same offset to retrieve the distance of LMC. And also you can see that the distance of anomalous Cepheids are statistically smaller. Then we also used the relation to calculate the distance between LMC and SMC, and as you can see here, also in this case, anomalous Cepheids are giving us a distance that is statistically smaller than the accepted one. So probably this is suggesting us something. Indeed, the last indication comes from the Draco galaxy, the Draco dwarf spheroidal, because this distance is well known, and with anomalous Cepheids we see that this distance is intrinsically smaller, so this means that we need to apply a correction for metallicity also for this kind of pulsating star. And in November we will start doing this thanks to Foremost. Whereas these are my conclusions. Nowadays, the most accurate H note is coming from the late universe, is based on classical Cepheids 3 run from shoes. But we are pushing a different one because the Type II and anomalous Cepheids follow the same physics that we well know, but they are based on a completely independent sample, so they will give us different information about statistics and systematics. Whereas, just to let you know, thanks to LSST, we will also be able to observe Type II Cepheids because we simulated the observation of Type II Cepheids. We will be able to observe them in galaxy hosting supernova 1A. And as you can see here, after 3 years of observation, we will be able to retrieve a period for these stars and also a light curve in E-band. So, thank you for the attention. If you have questions.
For questions or comments?
Thanks very much, Teresa, for the nice talk. I was wondering, so obviously the calibration of these stars is what you presented today, but to make the link to the Hubble constant, it somehow needs to attach to things that are more distant. So could you please comment on how you intend to achieve that?
Yes. First of all, we want to analyze light curve of Type II Cepheids in NGC 4258 because this is the last anchor that we miss for the first run, and thanks to this next observation, we aim to have light curves in galaxies where there are supernova 1A to do direct this link. But also we can just compare and move each note.
So how far do you think with James Webb or with HST you could take anomalous Cepheids or Type II Cepheids, given that they're intrinsically fainter than classical Cepheids?
Yeah, they are intrinsically fainter, but we did this exercise, and I think that with anomalous Cepheids we can arrive up to 115 kiloparsec. Whereas with Type II Cepheids that are more luminous, we did this simulation for up to KK 258, that is 2 megaparsec far away from us. So after 3 years of observation, we will be able to see Type II Cepheids up to 2 megaparsec. And we can also have the period with that percentage error. So I think that we can do something.
So which statistical tests did you run to make sure that these are The plot in which you were showing the two populations, I think one of the last.
No, this is Anomalous Cepheids in LMC and SMC. And we use this to calculate the distance among the two clouds. Because once we have the 0 point in LMC and the 0 point in SMC, we can just do the difference and we will have the relative distance among the two clouds. So they are different because we observed some in LMC and some in SMC. If you want to know the difference among first pulsator and first overtone pulsator, it's because they have a different, like you, when we observe them, they have different shape. And this is in near infrared, so the amplitude is very low. In principle, you start analyzing them in optical. For this reason, also with the LSST, I did simulation with optical, because in optical you have highest amplitude, and you can see the different lectures, and you can also see which kind of star are you analyzing.
Yes, if you need also to add color, so shouldn't that be, is that something significant? Because otherwise also if you should have, instead of averaging over color, correct for each color independently.
Do you mean correct for color? If we correct?
Because you said it's a period luminosity color.
Yeah,
and you
yeah,
saw that it's very different.
yeah. Indeed, nowadays we use in the extragalactic distance scale the period Wesenheit, where we need to assume only an extinction law. We assume an extinction law, but then we no more use the extinction and the reddening. So this is because period Wesenheit is in principle parallel to period luminosity color and allows us to do the projection with the smaller intrinsic scatter. Yeah, but when every time that we do like this, we fit a linear fit, we are averaging over color, yes. And we just do this, and we try to have as many as possible pulsators in one period luminosity.
Thank you so much for this.